Hey, welcome to the next experiment. In this video, I want to show you a walkthrough of this new resource, how you can access it, and what it looks like to make discoveries within it. Let's dive right in. The first thing you need to do is navigate to datadrivenhypothesis.org. You'll see a landing page that looks like this. The simplest thing to do is input your gene of interest here. There's some example searches. You can also browse pathways. One of the things I'll show you later is that you can search multiple genes. Or if you don't have a favorite gene, you can go ahead and click lucky. This then is going to lead you to a series of cards, a summary page of all of the data within data-driven hypothesis. We have two different versions of this. This is the public-facing version. We also have a private version that's under development. So there we have some new features that we're working on rolling out. The first thing we could see is that our gene is PhD finger protein number 8. This is a short summary. It looks like it's a histone lysine demethylase, and it requires iron and alpha-ketoglutarate. A great example. All right, we can also link out to gene entry. If we come down to protein, we can get some more information about the protein. This is also the protein summary and some links that link out to PubMed. We can get some expression information, say where is my gene expressed. In this case, it's going to query the subcellular localization. We can see that this looks like the protein is expressed in the nucleoplasm. Okay. Then what we can do is we can come over to plots. This is the dependency information that the last video talked about, where we are using the Broad's depth map data to look at gene dependencies. It looks like the PHF8 is not dependent in any genes, and it has a profile that looks like this. I would say that these cells tend to lose some fitness when this gene is knocked out, but overall, this would not be considered an essential gene. At the other end of the spectrum, we can see that there aren't too many cell lines where you knock out this gene and you see an increase in growth, maybe a slight gain in fitness over here. Next, we can look at our computed density curve to look at the distribution in a different way of where our dependency scores are for this gene. And then finally, we can start to look at the cell lineage dependencies. So what are the genes that are represented down at this end, and do they represent any cell lineages? So we can look here, and we can see that there really aren't any strong patterns. We can split this into sublineages. This makes a new plot, and look and see if any patterns emerge. From my view, I don't really see anything too strong. Maybe meningiomas are going to rely on this gene more than other cell lines, let's say carcinosarcoma or chondrosarcomas. We can then look at the raw data table down below by clicking on this link here, and then we can flip or even filter by clicking here, saying we want all of the genes that are, let's say, less than 0, just as a good start. Okay, so this is a way to look at some of the raw data and look at the relationships between dependency and these different cell lines. If we then come down to coessentiality, this next tab is going to identify genes with similar dependency values as PHF8. This is nice because this allows you then to look at the genes that behave similarly. What are the genes that have the similar pattern as essentially this plot? The way that we do that is taking a zipple correlation. And that correlation, then we can look at the z-score distribution of that correlation to get a sense of whether that's a strong correlation or weak correlation. We can see here that we have 19 genes with similar dependencies. So here's all 19. One thing that I've found is that there's some genes that have 1,000 genes as codependencies. And these are pretty weak signals. And so I can filter out genes with more than n number of associations. So let's say 300 and see what happens here. We go from 19 to 9. So these 9 might be the strongest 9 in this list. And that's just one way to try to filter out some of the noise. These olfactory receptors are oftentimes noise, and so maybe this filtering wasn't quite strong enough. But another way to look at the dependency values is to build a network graph. What's happening here, so it takes the top 10 here, and then it gets the top 10 of those top 10 and builds a graph out of it. And what happens is we see that in the top 10, there are no genes that have PHF8 in their top 10. So this is a weak example where the dependency data isn't telling us so much. One thing we could do is we can increase this a little bit. We could say, what if we increase it to the top 20? Are there any genes where the top 20 are in the top 20 and so on? And this still is an outlier by itself. Remember, there were 19 genes, and none of those top 19 have PHF8 in its top 20. So it doesn't mean that there's nothing here. It just means we might deprioritize going after this hypothesis. We can then look at methods if you want to see what I did, dive a little bit deeper. And then one last thing that you can do is you can download a report. The report then is going to pull all of the information, all of the plots, and all of the data in order to put it in a zip file so you can drop it into a presentation. So that's it. Super fast, super simple. Turns out PHFA wasn't a great example, but the point is to show you how you can march through some of these tabs and these steps in order to try to come up with new hypotheses. As time allows, I'll make some more examples of these videos showing how we can use this for biological discovery. So one more thing before we go. Here's an offer to you. If you want to take your favorite gene or favorite pathway and sit down with me, we can march through our development site, which has a lot more information that we're working on fine-tuning and curating. So you get some new hypotheses out of it, and I can get some feedback on how we can continue to grow this resource. Let me know in the comments below.